games, and we're really strong in reinforcement learning. So one of these particular low-level ways to build up AI systems. On the robotics side, we're a much smaller presence globally. We have intelligent prosthetic arms, Patrick. We have visual servoing by Martin Magerson. We have Hong, who's interested in actually a bunch of things, including some oil sand stuff. I think he's does a lot more vision stuff these days, I think. There's just people in engineering. Like our robotics presence is more dispersed. But actually, so much of the robotics world, much of the traditional robotics world is less focused on AI, right? They're focusing on mechanism, on sensors, and there's great advances to be had there. Sorry?
Satan has an excellent robotic work.
Could be.
Yeah, no, I just went to go visit there a couple of years ago. It was quite impressive.
Right. And like there's other stuff that I'm not as aware of in like our larger community, right? So my focus has always been on the AI side and robotics as an approach to AI. And actually, if you go to the big robotics conferences like ICRA and whatnot, the AI is a tiny portion, right? Because many of the traditional symbolic techniques only work to a limited extent, if at all, when they confront the real world. And many of the more modern techniques are just starting to be integrated into control methodologies for robotics. So that's what I can say for it. And yes?
Anybody trying to apply this into biomedical?
Patrick. Patrick is actually explicitly building, so Patrick is a professor in medicine, but he spent a lot of time, he's also still part of the ROS Edmonton. It's hard to get all of the relevant parties interested, right? So understanding what the AI can do and meshing that with what the needs are in the field. And so Patrick is one of the people who's basically leading this charge into building smarter medical devices. There's also medical robotics, which is a huge industry in and of itself. So they get Johns Hopkins is where they have Da Vinci, and there's like other very well engineered systems, because that's what often they need for things like surgery. And like when you're swallowing robot pills that will measure out your insides, you're concerned with how it reacts, and so there's a lot of the biomedical stuff. Maybe some of that I think is also going on. I don't know. There's lots of stuff which is sort of only tangentially related to AI, and so I'm not as aware of it. But other people are, like Patrick. Patrick is probably tuned into all of the stuff.
I think at the start they've done like, because like healthcare is like an overall like research thing that the ASUML works on, right? So they did like the scheduling stuff, the like tumor detection stuff.
Right.
There's the like
robotics and
overall.
manipulation as well.
Yeah. I mean, a lot of this is just like data analytics. It's not necessarily robotics, but they can have in the center as well.
Right. So it's much easier and much safer to work on the analytics side where you're analyzing the data as opposed to poking and prodding people where the ethics concerns actually rise substantially for some reason.
What about limb replacement?
Limb replacement. Patrick, what would you like to say about limb replacement?
Limb replacement? Yeah, it's a good idea. For the most part.
Except for the students working in the lab.
They're not allowed to replace their limbs.
Okay.
Stay here.
Okay, so let's just move on to modern AI and robotics. And this is just going to be like 50,000 foot survey, right? So in some sense, just to give you a sense of what's going on, AI and robotics are typically focused on different ends of the spectrum of engagement. So if we look at AI, well, much of the work is focused on things like language and reasoning, right? And this was like all that work in the 60s. It's what people conventionally think of when they say AI. Okay? Recently, like starting in the 90s and now learning has become dominant in AI, or maybe it's now dominant in AI. It's like at least a good fraction of papers at AAA. Whereas in robotics, the emphasis has been on the bottom up. It's on physical embodiment. Like how do you actually, what are the materials you use? How do you get the power in? How do you make better joints? How do you make better actuators? How do you make better sensors? And how do you integrate everything so you don't need a brain? Right? Like how do you just make systems that work is in fluid and nice ways that various biological organisms do, or even better than biological organisms do. And there's sort of this piece that I call safety and survival, which is often ignored in AI, but is crucial in most robot tasks, right? Like how do you make sure that your system survives? Right? How do you make sure you get to your charger on time? Or how do you make sure that the robot doesn't pull itself apart or destroy itself? Or when it destroys itself, how cheaply can you get new parts? When it destroys itself. Okay, and then robotics has slowly been adding little bits of learning. There's more model-based reasoning. But, it's a small fraction compared to the amount of emphasis that's put on the bottom. Okay, so traditionally these two areas are looking at systems from opposite angles, and so we get different emphases. But let's look at what McCarthy had to say about what is AI. Can we get a good definition of it? And, well, maybe. So, what is AI? It is the science and engineering of making intelligent machines, especially intelligent computer programs. It is related to the similar task of using computers to understand human intelligence, but AI does not have to confine itself to methods that are biologically observable. Yes, but what is intelligence? Intelligence is the computational part of the ability to achieve goals in the world. Varying kinds and degrees of intelligence occur in people, many animals, and some machines. Isn't there a solid definition of intelligence that doesn't depend on relating it to humans? Not yet. The problem is that we cannot yet characterize in general what kinds of computational procedures we want to call intelligent. We understand some of the mechanisms of intelligence and not others. Okay, so it's saying that the problem of intelligence is somewhat harder to properly characterize. And we accept this, but we want to build a better understanding of it. We want to build a better science of it. In some ways, we're still there. We might be at the point where, as researchers, we could start to formalize it, right? But it's still an ongoing process, and this is coming from one of the founders of, let's say, the symbolic approach and logical approach, John Carver. Is the guy responsible for this, if any of you guys had a chance to use that in the past? So what is intelligence? Intelligence is the ability to achieve goals. So the phenomenon of intelligence, like what we want to call intelligence, is that there are systems in the universe that are well thought of as goal-seeking systems. So it's really just us calling something a goal-seeking system because it's convenient for us. Right? What is a goal-seeking system? Well, William James, a famous American psychologist, referred to it as constant ends from variable means as a hallmark of mind. It's like what we would call, we would say something has a mind if it's able to achieve its ends from various situations, and it's a system which is best understood in terms of outcomes rather than mechanisms. It's easier to think about it as having a goal instead of thinking about all of the different computations or the processes involved in actually allowing the system to achieve that goal. It's like Patrick wants to turn his head left and right. How he comes to the decision to turn his head left and right is rather obscure. But he seems to want to turn his head left and right. And so this sort of gets further than us, but we could start to analyze it at the level of signals. We could say minds are sensory motor information processors, sort of taking a step away from the symbolic side where we say let's disconnect ourselves from the signals of reality and say, no, let's accept the signals coming in and say this is, the problem is really at this signals interface level. The mind's job is to predict and control the sensory signals. Okay? So that's independent of what's actually going on in the world or what we think of as going on in the world. This is really what it is. And when we take this approach, we can basically say, for any particular environment that we'd like to deal with, be it robots or chess, or buildings or websites or cell phones, we don't really care what the source of the signals are, we don't really care what the problem is. The only thing that we have to do when we're working with, or trying to build an AI system, is to say, these are the signals coming in, these are the signals going out. They define the reality for our system. We should assess the system's performance and express our objectives at this interface level, right? So this is kind of like adopting the philosophy of the matrix, where it's all just sort of numbers going in, and you say, you know, the signals are all that there is, right? Everything else other than the signals is just a story of how the signals came about. And this is a very useful way because it frees us from the burden of describing the worlds perfectly for the robots. Right? And in another sense, all of our machine learning technologies are implicitly doing this. And we shouldn't think that they don't have access to the world except through the signals that are coming in. Okay, let's skip over that. Okay, so maybe this last little bullet is useful. It's to say, when we speak of intelligence, we shouldn't speak of this as an absolute property, like this thing is intelligent and this thing is not. We should say it's a matter of degree. It's a matter that we're saying this is something that we're measuring relative to some particular objective that we're giving. And it's relative to an observer and a purpose. So it's really in the mind of the observer. So you might call this cat intelligent and this other person might not. You know, you might think that your child is smart and I am free to disagree. Okay? But like it could depend on the task, right? So maybe your child is really good at cleaning up their room, but they're not so smart, or they don't seem to do as well when they give them a calculus. Conversely, a person in university might be really good at answering the calculus question, but might not know what cleaning is if you shove them into it. That might be me. So the changing face of AI. So the focus of classical AI was on this formalization of abstract human reasoning. And the thing there is that people were providing this matrix and saying, this is the way the world works. Like, you're going to see a cube or a triangle, and you can push the cubes, but you can't push the triangles. The focus of modern AI is to learn directly from these signals. And the advantage is that the data provides the semantics of knowledge. Right? So it says, let me push it and I'll tell you if I can push it. Right? Let me try pushing it and I'll tell you if it moves. And if it moves, then it's movable. Right? It doesn't matter whether it's a triangle, sphere, or a tree. Okay. Now, I sort of set this up as a dichotomy, but that's not really the whole story. Modern AI systems typically require bits of both. The relative amount of human provided knowledge from the human guidance is diminishing. And this is the real win for us. Because this is how we get machines that can play Jeopardy. Right? The amount of human experts that you need, none of whom would do particularly well on Jeopardy, is like a handful, but the databases of knowledge that they use are vast. And so we can expect this to scale up. Reinforcement learning. This is getting long-winded, but because I like it, I'm going to drag you through it. Just some high-level bullet points. So it's an approach to AI inspired in part by animal learning, so it's not referring exactly to the animal learning experiments, it's just inspired by it. There's several things that are part of it. One is learning to maximize long-term reward. So if you specify a task, you can learn the control behavior, so as to do well at the task. Learning to predict long-term consequences of behavior, so a prediction problem. This one, learning environmental models and reasoning with them so that we can start to do sort of planning and the inference that we do with the human-provided models. We can also support human-provided models and features. This approach has been useful in multiple disciplines, so it's useful in robotics, typically with human-provided models. Recently with less of that. Recently more with just rapidly learning from experience. It's useful in AI. It's neuroscience control theory. There's been tiebacks to the way that humans and animals actually do behave in terms of measured neuroscience signals, dopamine in particular. The nice thing about this is the tasks are very well specified at the level of input-output interfaces. The challenge is actually specifying your task in terms of the input-output interface. Like, be good is a sort of hard thing to define in terms of continuous signals, or make me a great souffle is a hard thing to specify in terms of those signals. And it's an active topic for ongoing research. Okay, so that's the big heavy stuff. Let's do some of the lighter stuff. Questions about AI? Yeah?
Can you get me up to date, or what's the current status of the financial robots, financial engineering that crashed and burned 10 years ago? Are they doing any better now?
You mean the high frequency trading?
Well, that's one technique. There's many people have come and sold us, oh, we have these robots that will go on and trade futures, and you can make money overnight while you're sleeping.
I see. So,
Believe it.
again, this is an area in which I don't know much, on almost anything. So there are, again, finance people at the U of A, and some of these RL ideas, or reinforcement learning ideas, have been used in trading and finance.
What drives me is I met some of the guys behind ROHM. They're at Alliance, that's next to Apple in California. And the four guys behind it, they made their millions to start the company by trading futures. See, that's why you need to do this.
Yeah, so you might make money and you might lose money. The markets don't obey most of our standard assumptions, and so if things work, it's not because it's well founded, it's because it's just happened to work. So I wouldn't get into the finance industry with.
I believe it works for a while, and then the market compensates for it, and then it doesn't work anymore.
That's not bad, because there's, in the 70s, 80s, there was the fast Fourier transform to break down the market periodicity, and that worked for a while. And like in the 2000s, they had this financial engineering, and it all crashed. Long-term capital had 2 PhDs behind it, and it almost broke down the entire financial system. They had the robotic over. They were leveraged like 200 to 1 until it didn't work.
That was more artificial intelligence rather than robotics.
Well, artificial intelligence, I don't know what these were intelligence.
These are just, I think that
Okay, so that,
we're not learning.
can we get any better at this? Have we got something that works now?
I would not put my money into such ventures. So, yeah.
There's no answer.
Finance is it's much more like game theory and other things. It's
DARPA interested in AI?
is DARPA interested in AI?
Yeah. I mean, I know they're interested in robotics, right?
They're also interested in
Do they
AI.
have challenges with that? Because I saw the DARPA robotics, but that's, I did not know very.
So DARPA was a major funder of AI, maybe the primary funder of AI in the U.S. from its inception.
Do they have challenges with this? That's what I think.
Oh, the AI challenges. Yes. So it's not on the robotics side, but they do things like managing databases and managing inference. So when they're trying to mine all of the interconnections between people to say who's a terrorist or who's a likely target, or like how are these people interrelated? How do you do deep inference? How do you do translation? DARPA is involved in all of this.
So that's data.
Yes. So I've been giving you sort of the AI robotics slice, but there's many other slices to AI, right? It's it's not all, robotics is a thin slice of AI, learning is a growing slice of AI, but reasoning is a large portion of AI, language understanding is a large portion of AI. There's many pieces. Okay. Yeah, I've been focusing on robotics. Okay. Any more? Maybe? I'm talking too much more than I expect. Okay, ROS is a lingua franca. So, by which we mean what? A language for communicating between pieces, and ROS is good. So it provides us interfaces. It also provides us, in some sense, an operating system. Right? It's a system which has a bunch of libraries for communicating. And if you have an operating system on your computer is typically much more useful than if you don't have an operating system. It gives you a bunch of standard services, and these standard services are hopefully improving and getting better and more capable over time. This is the premise, if you will, behind ROS. It provides both of these. A set of libraries that are robust and improving, a set of interfaces for communicating between the components, often, like, much of it at the level of sensors and motors, some of it at the higher level. Okay, but I want to focus more on just as a communication language. So I think that's maybe where the things are best for AI. Right? So it's a common language within robotics for connecting things which are used in multiple places. So things like a robot's geometry, its physical geometry, it's where the motors are, what they're connected to, where the sensors are placed, how the observation models work, how the dynamics of the robot work. These are all different attributes of your robot, and you might want to change them. Right? You want to put on a different sensor from a different vendor, put on 3 sensors instead of 2, have 5 arms instead of 1. Right? Or 8 arms. Are 8 arms okay? Maybe. But then there's all of the visualizers, right? There's all the things that you could do with these different kinds of data. So ROS comes with visualizers, it comes with motion planning techniques, collision detection, mapping, localization, and data logging. And much of this is infrastructure. The parts which are perhaps, well, mapping and localization I pointed to as being a fairly recent advance, this sort of mix of AI things in here. Actually, the motion planning stuff is also taken off of the AI groups, or collision detection, so lots of work in the 80s and so and ongoing in terms of figuring out how a robot can plan a path to a destination and what works. Now the advantage of ROS here is that you can simplify reuse and code maintenance across these projects, groups, and time, hopefully giving us a stable base. Because when I started as a grad student, we had 2 robots, and like basically all the code on one was written by hand, and all the code on the other, well, we had some libraries, and then it was mostly all written by hand on top of that, and then all the grad students left, and all that code disappears, and it's not shared, it's not reused, people reinvent the wheel. But when there was really a small number of groups, you can't really prevent that because the robots are changing so frequently. Now we have some standardization, right? So ROS really is a lingua franca, I'd say, in the robotics field. Now, what does this mean for AI? Well, it provides a bunch of standard interfaces to all of these different systems. And this, in some sense, is the great win because the AI doesn't care where the signals come from, provided that it can get with the signals. And actually, writing the interfaces for all of these sensors and motors and algorithms is a pain and it's hard to get right. And if you can just say to your AI or learning system or control system, say, okay, this is some task that I want you to do in the larger system, right? Can you predict where my arm's going to be? Can you reduce the amount of power that I'm using when I'm performing this task? Can you allow me to perform this task faster? Okay? And then the AI doesn't have to worry about all the communication protocols. It doesn't have to worry about which systems you're using or the fact that you swapped out one robot for another. You can just say, at the level of signals, I can now make this thing better. And we can simplify the life of the AI engineer because most people who work in AI and machine learning don't spend so much time with robots. They don't want to spend time with robots. They know that the robots break. but they have some really good algorithms, and we'd like to be able to transfer, right? We'd like to be able to say, here are some good ideas, ways we can make a system better, if only we could hook into the system. And so ROS might provide a simplified interface. And there's some bits of this in ROS, right? But it hasn't penetrated too deep. So in Move It, we have, I think, occupancy grids, search-based planning, recognized planners. So these are a bunch of AI techniques. And in navigation, we have much of localization, occupancy grids, and feature maps. More recent AI research is often at the fringe, so these are a bunch of reinforcement learning packages that have been written for ROS, but you won't actually find them listed on the ROS main page. Right? And so there is still limited support for AI in ROS, but there's the potential for much more. In part, this is because most AI algorithms haven't been attached to a robot ever, and so they're also not in the ROS library, but I expect many more of them will be. And it comes about because, well, the concerns have historically been a little bit separated, but now we're getting to the point where, well, maybe the algorithms for learning and reasoning are sufficiently capable that they could provide some real benefits for robots. And actually, this is what we're finding on the research. Right? So it's not yet at the commercial level, but maybe it's, I don't think it's at the commercial level. Maybe not, depends on what Patrick's doing. But we're getting to the point where it's measurably useful. Right? We're able to see real advances to it, and so we can think of connecting it up. And that brings us to the future. What does this mean for people who aren't in academia, who wish to sort of explore what they could do with these things? Here again, I'm going to say this is promising. Good warning, some these are all personal opinions. Take everything I say with a grain of salt. And maybe the important thing for you to realize is there is no consensus amongst the experts as to what's going to happen and when it's going to happen. Okay, so if I'm optimistic, you're going to find 5 people who are not. Okay, so just because I say something that's going to happen doesn't mean it's going to happen. Okay, this is far too small. But main point, what are we seeing in robots and AI? The robots are cheap and easy to develop, which means that we see low cost and broad exploration. So basically everyone can buy computers, sensors, and actuators and look at automating their processes, whatever they are. Right? So farmers are doing this, small businesses are doing this. And actually it's sort of surprising to see where things go, right? So the Internet of Things is taking off. Everyone seems to be playing with drones these days. There's all these maker movements. Everyone's sort of involved with the sensor and actuator level and like building things. Okay, and then we also see companies, right? So we see small startups and venture capital funding, like big business interests. We also see those things that I'm barely aware of, or wasn't aware of. Automated dairy farms. Got 500 cows and it's robots taking care of everything. And this is like in Alberta, but the robots are, I think, coming from the Netherlands. There's automated trucks in the oil sands. I think the oil sands, one of the companies just bought a bunch of automated big trucks from Japan, some Japanese company. Kibo went to Amazon. Baxter is being sold as a pick-and-place robot. It's continuing to advance. DeepMind is one of these recent startups in London, actually. I'll be joining them. Boston Dynamics, another robot company bought out by Google. They were the ones making robots for the Drug Robot Challenge. And so that's on the robot side. What's happening on the AI side? Our recent methods are being designed to benefit from large-scale data, which is coming in from all these sensors and going out to motors. And it requires limited amounts of human collective knowledge. And so we see improved, and just speak about reinforcement learning here, we see improved methods for both prediction and control, for both learning and reasoning. We have domain-specific improvements. This is not MRL, but this is with the deep nets with language and speech and image processing. We see cross-domain methods improving as well. So basically, they're each independently getting better. If we look at what's next, we're seeing better performance across multiple real-world domains, and this is in some sense new in terms of the speed at which the advances are coming. Now, while they're tackling many more data streams, I think the algorithms are only slowly becoming easier to use, so it still typically takes expertise with the algorithms to make them work properly. But that's slowly improving, making easier and easier to use. The hardware is becoming more available, so I expect that our AI systems will slowly start providing benefits even to naive users, right? So we might get to the point relatively soon where you could hook a prediction algorithm to your motors and sensors and actually have those predictions be interesting. Or say, I want to do this task 5% faster, and if it's an existing system and it's just tweaking the parameters a little bit, it will probably work. Right? Now, this plays off with the ease of use. If an expert goes in there and understands what's going on, they can typically find out where it's going to be helpful, or project where it might be helpful. But as things become easier to use, we might see this more and more broadly. Right? So maybe your irrigation system uses less water. Maybe your Nest home thermostat actually figures out, I don't know, like when you're around or when you want a room to be warm. Maybe your lights turn on before you get into the room. Okay? We should realize that we're sort of awash in data, right? Or at least we're potentially awash in data. And if the systems could just learn little bits about it, there's potential for making people's lives better. Okay? And part of this is that, well, I expect that our AI solutions will slowly start to carry more of the knowledge burden, right? That if they can autonomously learn the knowledge required to do the well-specified task in a better way, then you don't have to know as much about the way the system works. You say, here's the system, I don't have to tell you how the world works, you can just figure it out. Okay? So that's a soft state, right? We're just going to get things to be a little bit better, but maybe it will accelerate over time, and that's sort of what a lot of people are excited and concerned about. Right? So a couple of profs at MIT put out this book called Race Against the Machine, which sort of forecasts many job losses, but a more productive society, and wondering what this will mean. Nick Bostrom wrote this book called Superintelligence on basically outlining his concerns about having super intelligent machines and what this will mean for people. I take it with a grain of salt again, in a different direction. Many people talk about the singularity, they have different notions of what this is. Bernard Ringy pushed the term, coined the term, and I think he speaks most coherently about it. I'd like to say, like, no one knows what the future is, but we can help to shape it. Okay. Yeah, let's skip this next one. Yeah, so maybe at the highest level, perhaps robots in the future learn to perform any task a person would perform, right? That's what we like in terms of AI research, is just understanding what's going on, right? Understanding how you learn, and understanding well enough that we get a machine to learn like a person learns. Okay? And this would have some societal consequences, right? It would change the way we think about jobs, leisure, and culture. This has happened in the past, right? The Industrial Revolution, agriculture, not always pleasant times, but you know, if a society makes some wise choices as to how to look at these technological changes, then they can benefit from it. Poor choices will lead to less happy societies, right? Japan outlawed guns after they said, like, we don't like what this is doing to our society. It worked for them for a couple hundred years. It didn't work for maybe 100 or 200 years, and then they seem to be doing okay. But, yeah, these are choices. The future's not written. It's just having smarter machines is not going to make life nirvana or hell. Right? But what are these choices? So we're not there yet. So I'm saying, what are some fanciful questions for future generations? Right? Like, what might this mean? Should a robot get a vote? Should a robot own property? Would you put your brain into a robot body? Would you augment your brain with an artificial prosthesis?
Tomorrow?
Would you make a clone of your brain, and what would that mean? So here's a slightly more pressing one, because people are starting to think about this and wondering, like, it's hard to make a decision on it because no one really has a clear definition of AIs yet, right? And it's sort of merging with, there's a somewhat fluid boundary between people and machines, right? We use glasses, we use hearing aids, we use pacemakers, we have artificial hips, we have artificial prostheses, we might have artificial pancreas, like, but we might also have these virtual bots that are doing finance. And the question is, well, where do the laws pertain? How do we apply them? What does it really mean? Like, can you meaningfully punish it or say that these laws apply? And if you can't, then what purpose is there in making those laws? We should figure out other ways to structure the system, right? So, like, and we already encounter some of this when we deal with multinational companies, which can wander into one country, do things, leave the country. You know, there's not necessarily a person that you can put in prison, which will change the behavior of a multinational company. And because this is changing the way, like, this is changing the way that we deal with other agents. It's a complex question. It has no simple answer. But we don't have to really answer it, right? We might write stories about it at the current point, but we're nowhere near the point where we can actually define it usefully, right? Because in some sense we haven't experienced AIs yet, right? In the more fanciful forms, and often we are led astray by our science fiction in terms of what we understand. Sometimes in some sense we don't understand it well enough to legislate. So the summary of this sort of future is technology has changed our society in many ways, and robots are only just part of this ongoing process. And we can choose to develop forms of technology that we need to use, right? So we're people, we need to make choices. Yeah, but this is the future. So, thanks.
Does anybody have any questions for Joseph?
Yeah.
I have a question. Short one, maybe not short. So we look back and we see things like Shaky.
Yep.
And a lot of perhaps why Shaky had to sit and think for 15 minutes or half an hour or an hour before making choices is partly computation. So if we look back then and added the level of computation we have now, would everything have gone much faster, or were there still really fundamental ideas that needed to be hashed out that even computation couldn't solve?
It would have gone much faster, but it's still dealing with polygonal worlds
Yep.
and models of the world which are all given. In many ways, this is still the fundamental approach taken by many things like in the Amazon Place Challenge. They're just operating much more quickly with much more sophisticated models. Remove the guys. They are operating much more quickly with much more sophisticated models. The ability to learn directly from experience, the ability to deal with an unstructured world, right? Like digging a pile of dirt or playing with sand, you know. These are hard things for us to specify how things work, right? We don't have good analytical models of them. It's better if the robot can learn these things directly. Right? And so, how to clean up a pigsty, right? This is not something that the shaky-based models would be particularly good at. Right? that you need to learn from experience. You need to learn from experience and acknowledge that your models are limited. Right? I expect the more modern approach will do a substantially better job. These earlier versions, like Shaky, might be viewed as crude approximations to what we are really interested in.
I see a lot of the advances in both AI and robotics as being highly dependent on the hardware that's available. Right, the original transistors, and then microchips, and then embedded systems, and so on and so on.
Right. So
The fact that Shaky was able to do what it did at the time was entirely dependent on the hardware that was available at the time. So yeah, now that we've got significantly faster machines to be able to handle that computation, yes, it will go faster for that reason. But again, there's still all the different models of computation that
Right.
needs to deal with. And then the future of robotics will be equally dependent on all the hardware that will be available.
So it is dependent on the hardware, it's dependent on the computation, sensing, and actuation, but in the long term, I think this is just one of the legs on which it stands, right? It's like a stool with 3 legs. Computation is one of the legs, and reasoning with faulty models or partial models is another one of the legs, and then learning from experience is another one of the legs. And actually, the place where we've been the weakest has been learning from experience, and we're getting essentially better at that. And, the connection between our learning and our reasoning has been historically weak. People are working at the research level to bridge that. It's hard to say how fast that will proceed. People are working on it. Yeah.
Reasoning seems to be, at least from the stuff that I've encountered, predominantly engineered. So when you're dealing with situational stuff and things of that nature, it's hand-coded by the person, and when you're doing the reasoning, you're resolving these things and searching through what you perceive in these engineered models, as opposed to, the experiential stuff where you're updating from these environments. So how do you reconcile the differences between these two? Well, obviously you need both, or a blend of some form of the two to be able to do something at a higher level.
Right. So blending them is still ongoing research, right? There have been successful demonstrations of it, including things like IBM's Watson, Solving Jeopardy,
Yeah.
is a good mix. But it's still challenging. And actually, many of the competitors in our robotics challenge, I expect, use a mix of learning within a model and learning model parameters, right?
Okay.
And fitting these rules. And so it's often a mix, and hopefully we can make. The challenge with this mix is that it really requires experts to step in and say, these are the models that we can learn, this is how to parameterize everything. The goal of making everything more user-friendly, so you can just say, here it